Alright, so again, the plan is to go over the drawing from last class, look at all the construction numbers again, and then as we're going through, we're going to talk about calculating the HTM at the same time so that we can fill in the rest of this sheet and get all the way down to all our construction done. That is the majority of the legwork in a load. After that, well, infiltration takes a minute too, but most everything else is just inputting numbers and adding things up. So it is a lot of the meat of it, because obviously we've got to figure out how much heat we're losing through each building component. So let me switch to the drawing real quick. Alright, so if you guys remember right, this is the house we were working on. First exercise we did, all the dimensions in, everything there, and these are the constructions we had. So as we go through each thing, I'll note what the construction of it was again, and then go to the table where we find the construction of it, and we'll see where it's highlighted again from the last class. Alright, so let me do this.
Emily wanted no chicken skin.
Okay. What we'll do is, let me go ahead and share OBS again. That way you guys have got that and it's a little bit bigger. Alright, so going back to Windows. Alright, our windows right here were double pane operable clear glass wood frame, no external sunscreen with Venetian blinds. For heating, the only thing that really matters is this double pane operable clear glass and wood frame. Because if we go back to the table, your first table, table 2A, remember table 1 is all about finding your design conditions. Table 2 is where you start. Table 2, 3, and 4 basically are all your constructions. So if we look at that, you're almost always going to be in this top set of tables, and we go down. This is clear glass. We go down to 1D-C was double pane operable or sliding glass door. So that is our window. And then we go under wood or wood with metal clad or vinyl down here, and this is our HTM, or sorry, our U value. So what you're going to find is that when we're doing heating, a lot of times we have to calculate our HTMs. With cooling, a lot of times we're going to already have the HTMs. Now manual J8 is a little different than J7 on this. If you guys, well, I know you guys don't, but if you've ever looked at J7, it was slightly simpler on cooling than even this, but heating has always been like this for 30 or 40 years. You've always been able to do it because with heating, the nice thing about calculating heating loads is we disregard any solar gains or anything like that because their effect only helps us in the winter. And because the days are so much shorter in the winter, even though it only helps us, it doesn't help us a lot. So we can actually get exact, basically, BTU values lost. So we always have to calculate this number. The older tables used to have it set up so that you could like round up to the nearest number and use that. But J8 doesn't give you that option. You have to actually calculate it out. But it's really easy, okay? So these are our U values. Remember, disregard the SHGCs. They're not important. You need this U value. So this U value is 0.57. So what I'm going to do is I'm going to switch over to Excel. And we're going to, just for convenience, so I don't forget as we're going to do it, I'm going to put that the U value for this construction is 0.57. So what that U value of 0.57 means is that for every degree of temperature difference, we will lose 0.57 BTUs for each square foot of that window. So what we need to do is take that and take into account what our temperature difference is so that we can get a heat transfer multiplier. That's how many BTUs we're going to lose through each square foot of window on a design day. So on the coldest day that we designed for, which is how cold it gets 99% of the time, right? We're going to have 1% of the time, we're going to have those days where it gets lower than 17 degrees. But for the most part, you know, right here where we're getting close to, right, the dead of winter basically, the 20s are really about as low as we get. So 17 is a good design degree day for us. So we're going to lose 0.57 BTUs per degree of temperature difference. So to get our HTM, and this goes for everything in heating is essentially going to be calculated like this. I can't think of an exception. Maybe we'll run across one because I'm forgetting one, but for the most part, everything in heating, you're going to do 53, okay, times that 0.57, 0.57, and that will give us our actual heat transfer multiplier to put right here in this cell. So 53 times our U value equals our HTM for heating. It's as simple as that. And then what we do over here is we do equals that HTM times our area. And that right there tells us that we lose 6,253 BTUs per hour in just the windows of the house on a 17-degree day. So now we have that number done. All right. And it's basically as simple as that. We're going to basically repeat that process all the way down through heating. Now, what I want to do before we get into windows and cooling is I want to repeat this process for all the heating numbers first and then go back to cooling. That way we kind of repeat this again and again, and we don't get lost looking at cooling because cooling works a little bit differently. Okay, so let's repeat this process again and go to our next construction that has an impact in heating. So again, the rest of our window numbers here are for cooling, so they don't count. None of these numbers matter right now. We're not doing that yet. We've already got our HTMs there, but I want to talk about them again, so we'll do that. We go down to our wood and metal doors. So let's look at that one again. If we go back to our house, just to refresh our memory, the door was a wood door with a solid core and no storm, right? So we go to our tables, we go back to that and find it. Remember, table 3 is all about windows and cooling. So if you're working on heating, you'll be skipping table 3. You're going to go straight to table 4 to get all of our opaque panels, right? All of the items that are, you know, basically not windows. So anything that's not windows is in table 4. Table 2 is windows and heating. Table 3 is windows and cooling. Table 4 is everything else, right? So doors are the easiest one here. We have wood and metal doors. We figured out the other night that we have wood door solid core right here is an 11D, right? 11D. So the U value for your wooden doors is right here next to it. All of these numbers over here are for cooling, okay? So disregard those right now. We're only working on heating first. So this U value right here is our our door in heating. It's a 0.39 U value. So solid core wood door will lose 0.39 BTUs per square foot per 1 degree of temperature difference. But we don't have a 1 degree temperature difference, right? I didn't go over to the other page, guys, sorry. Alright, so here we are. Let me repeat that a little bit. So if we, again, our wood door from exercise 1, I'll just flip through so you guys can actually see it since I forgot to switch the screen. We had wood door, solid core, no storm on that exercise. We go back, find table 4, And you really should be trying to follow along in your book right now so you see these things in your book and can flip to them. These are the most important tables to be able to flip through, as everything in that in this group of tables is where we're going to be in the book. Okay? Anyway, we find our wood door again in table 4. And remember, the calculations are right here at the top for us. Okay? If you forget how to find the heating HTM, at the top of that table it tells you heating HTM U value times indoor design temperature minus outdoor design temperature. Okay, so remember I told you right here that is your HTD, because we've already got that on our table, and we'll look at that again when we input the U value. I'll show you where that is on your worksheet. You should have this at the beginning of the job. All your temperature difference should be done before you even start pulling up construction numbers. So you don't even have to do this extra thing right here because you already did it. The indoor minus the outdoor is our heating temperature difference. Okay, so that's what we're doing. We're finding the door that we had. Here's our solid core wood door with no storm, so we're neither one of these. We're the one that doesn't have a storm. 0.39 BTUs. Alright, so as we're looking at that, go back to Excel, and again, just to make it easy so I don't forget, we'll put the U value right here right now. You can do this too if you want. You don't have to, but it's a good way to make sure you're double checking your work. So our U value for this is 0.39. And if you forget what U value is, there should be in your book, there should be a definition of it in the back. We'll talk about navigating books a little bit more when we get to code stuff, but of course if you never learned it in school, remember one of the best things you can do is use the definitions in the index to your advantage when navigating a book. It's very important with books like these, to understand all the definitions to a T, because the definition matters. What you think it means isn't necessarily what the book says it means. And then finding stuff with the index so that you can flip to things you forgot a lot. But if you read it, the last sentence is what I'm talking about. U values are expressed as British thermal units per hour per degree Fahrenheit per square foot. I want you guys to remember that. So if you want to flip in your book to page 266, you need to remember that a U value is BTUs per hour per degree Fahrenheit per square foot. Because if you memorize that, it should be easy to understand the math we're doing here. Because again, this door loses 0.39 degrees, or 0.39 BTUs, per degree temperature difference per square foot. So we're just taking this and making a heat transfer multiplier, which is just taking into account our heating temperature difference, which is 53. So again, on a 17-degree day, we have a 53-degree difference between the indoor and outdoor temperature. So we have to multiply 53 times 0.39, because that's going to tell us how many BTUs we're losing through per square foot of door on a design day. The day that we're designing for is basically our worst case scenario without picking the coldest day ever, because that's poor practice. Alright, so again, I'm using Excel to help me here, but it equals 53, okay, times 0.39. And I guess if it helps, I'll even do it like this instead of using the cell. It equals, I did flip back to Excel, right? Yeah. Alright, it equals equals 53 times 0.39. So, and there's your number, 20.67. Alright, and this is the advantage you guys will have if you actually use the Google Sheet or use Excel to do these. You know, we used to do this all on a calculator by hand, but if you actually use your computer or have a way to do this not by hand, that would be ideal. But if you don't, then get some of these sheets printed out and just write it all down by hand. So all you'll have to do is do this equation on a scrap piece of paper and then write it down in this cell. Okay, and then again we can go ahead and do equals our HTM times our area of our door, and that tells you that through all the doors in the house, which is only one door on this one, right? So through that particular door we lose 434 BTUs per hour on a 17-degree day. So as we go on, we're going to figure out all these numbers, and we're going to know how many BTUs we lose per hour for the whole house when we get to the end. And that tells us how big the equipment needs to be, because we have to make up the difference. So moving on again, let us switch back to the house for a second. And we're at our walls and heating. And our walls were 2x4 wood frame, vinyl siding with R13 cavity insulation. So again, finding that in our tables, everything's in order in the book in the order we find it on our sheet. So it should be the next thing we're looking at is walls, and it is. The next thing we're looking at is walls. This is no insulation in the stud cavity. We do have insulation in the stud cavity, right? We have R13. So we keep going. This is R11 insulation in the stud cavity. We don't have R11, we have R13. Keep going, 12C. There's our R13 insulation in the stud cavity, and there's the construction number we found, right? A 12C-0SW. That is a wood frame wall, R13 insulation in the stud cavity, no board insulation on the outside, wood sheathing, no board insulation, right? Our U value for that is right here. It's 0.91. So 0.91, or 0.091, sorry. 0.091. Make sure you don't screw up where the decimal is. It's 0.091. Commonly, your walls have one of the lowest U values of most of the components you work with. So again, like I was telling you guys the other night, that's the one, if you're going to get it wrong, if you're going to not have the exact value, even though there's a lot of wall, it'll still have one of the lower impacts on your load calc. So if you're not sure if it's R11 or R13, it's safe to say, well, it's just R11. You know what I mean? The biggest thing is to verify you have some insulation, because if it doesn't have any, you need to account for that. And honestly, remember, your job as a technician is to tell people if they don't have any insulation in that cavity, that before they make big changes to their HVAC systems, they should make energy efficiency changes to their insulation, because that commonly is a better investment than an efficient you can get a really efficient system to make up the 120,000 BTUs they're losing, but if you can get it down to where they're only losing 70,000 BTUs, then a less efficient system is still going to be better for them in the long run. So you always make upgrades to windows, doors, and insulations before purchasing a new HVAC system if possible, especially in older homes. And especially older commercial buildings, because commercial, it's even more of an impact. So I always recommend that first if it's possible or in the budget. Anyway, so again, let's look at that number again. It's 0.091. We will go back to our worksheet here. And again, just to make it easy so that I don't forget it while I'm talking, we will write the U value right here next to it. You do not need to do this, but it just makes it easier for me to make sure I don't make a mistake while I'm teaching you guys. if you do the actual worksheet, what you'll do is you'll create all these construction numbers and it'll give you a drop down list here. Maybe we'll look at that last class. We'll do it on the actual sheet, but for now, the simplified way of doing it makes it a lot easier to understand everything that we're doing. So if the U value is 0.091, then what we're going to do is under heating HTM, again, our 0.091, oh, let me go ahead and do this, equals our temperature difference, 53, right? Our temperature difference is 53 in heating, so 53 in heating times our U value, will equal our heat transfer multiplier. And you see how much smaller that is than a window or a door, right? It's very small. Generally, your walls are going to be a very small HTM. And again, we can go ahead and put that number here. What I used to recommend when you're working on this is to just do all this multiplication last. But since it's kind of all here on the sheet, it's pretty easy to just put in the formula. And if you guys don't know, what you can really do once you have this made up, you can just copy this cell and paste this cell, and it'll paste the formula for you. So if you just copy a cell that already has the formula in it, if you just paste it down here, it'll automatically copy the formula but move down the other way. So you can really just copy this formula all the way down. I'm just repeating it so that you guys see the formula done multiple times. But anyway, it's pretty easy to just go ahead and copy that down. So again, our heating temperature difference times our U value is our HTM. Alright. Ceilings. Let's look at our ceilings again, and we'll find that number. Pull up Bluebeam. Our ceilings were under a ventilated attic, R30 insulation, dark shingles. So we move on down. These are all more walls. We already found our walls, so we shouldn't be looking at any more walls. We keep going until we find where ceilings start. We're still in walls. There's a lot of pages of walls, okay? The walls have probably the biggest section besides cooling for windows, but cooling for windows, usually you're using that first table. Still more walls. Alright, here we go. We get to here, and for you guys, this will be on page 157. You get to this point. The first one is your most common one, okay? Your most common one is right here at the beginning. Insulated ceiling under an attic, okay? So we have an insulated ceiling under an attic. That gives us a 16B construction number. We move down. Really, the only thing you have to find before that is the thickness of the insulation, or the R value of the insulation. So the R value of our insulation is 30, and that's right here, R30. So there's our U value. Remember, these numbers are for cooling. Ignore those right now. We're only talking about heating. We're going to come and talk about those again soon. But these are U values for heating, so we use this U value, move back to our worksheet. Oh, I didn't memorize what it is. It's 0.032. 0.032. So, go back to Excel. Go on our worksheet. Next to ceilings, I'll put the U value so I don't forget. U value is 0.032. Put that in. Done. So to find the heat transfer multiplier, our heating temperature of difference of 53 times our U value of 0.032 is 1.7. To find the BTUs lost, multiply that 1.7 times the area. So multiply the 1.7 times 840. BTUs lost through our ceilings is 1,425. Exposed floors is our last one that we're going to work on in heating. The last thing we got to do is our exposed floors right here. So let's go back to our drawing, look at what kind of floors we were dealing with. On our drawing, we had floors over an open or ventilated crawl space, carpeted floors, and R13 insulation. We go back to our tables. We have a couple more tables of ceilings, so we're going to want to get through those. We go into floors over unclosed, unconditioned crawl spaces or basements. We don't have that, right? Our crawl space is not enclosed. So we want to go look at the next table and see what that is. And that's floor over an open crawl space or garage. So that is what we want. Open or ventilated crawl space. Okay? So we go down. The only thing we need to know besides that for our heating value is the insulation value, which was R13. That gives us a U value of 0.068. So we go back. Make sure you remember your U value. I'm going to write it down. Is 0.068. We're going to do 53 times our U value, and we'll get our HTM. So 0.068. And that gives us a 3.6. We have 840 square foot of floors. We're losing 3.6 BTUs per square foot of floor, right? On a 17-degree day. So that 3.6 BTUs per square foot of floor times our 840 square feet means we lose 3,027 BTUs per hour through our floors in this particular house. And that is all of our heating numbers up to that point. All our heating numbers are done. After that, we get into infiltration, which requires more preparation before we input the number. So this is where you basically stop on your construction. Generally what I do is get all these numbers first, then lay out the building, then get all these numbers. Oh, I didn't switch the sheet, guys. Sorry. Alright, it's too much switching between windows. Maybe on the next one, what I'll do is I'll set up a screen where they're both just side by side. I think that would be ideal. So I'll do that on the next one. But anyway, again, that's where I did the math there that I didn't show you guys. I'll go ahead and look at it again. Our U value was 0.068. You guys saw it on the other screen. So 53, which is this number right here that I highlighted the cell on. 53, which is our heating temperature difference, times the 0.068 gives us 3.6, times our 840 square foot of floor gives us 3,027. And then again, like I said, that's as far as we have to go right now. All these numbers is a couple classes from now. We'll talk about the rest of these basically. Alright, but what I was saying is what I do is you do all this first, because this should be the first thing you do. And if you live in Fairfax County, these numbers will all be the same. It doesn't matter. Every house you do, this will be the number you use if the house is in Fairfax. And for that matter, really use the same numbers for Arlington, Prince William. I think Loudoun has a slight difference on winter or something, but it's still basically the same. You can use these values for basically all of Northern Virginia and be safe. but make sure you check with the county on what numbers they want. But anyway, you input all these numbers first, then input everything from your house, find all your construction numbers, then find all your HTMs and calculate that over. And then once you get that far, we go to the rest of this, which, like I said, this is a couple classes away. So that's heating. With heating, every single construction is 53 times the U value times the net area. And that gives you your BTUs lost. Now, cooling is a little simpler or a little harder depending on how you look at it. The nice thing about cooling is there's a lot less math, but there's more things to remember. Okay? So you have to do less math, but there's more things to make sure you get right. And the reason is, and I know I've said this a couple times, but I'm going to repeat it. The reason cooling is a little bit more complicated is because we are dealing with not only the temperature difference between inside and outside, we're also dealing with the solar gains that we get, the radiative heat that we get from the sun. Okay, and we're also dealing with the heat stored in the ground outside, the daily range, you know what I mean? A city with a lot of blacktop, a lot of asphalt in it, is going to stay warmer longer than, out in a rural area where there's less things to hold the heat, okay? Less construction. So those are both a little different situations. There's a lot of other factors in cooling is what I'm getting at, right? So since there's a lot of other factors in cooling, you can't just say, oh, the temperature difference times our U value will equal the BTUs gained. It's not that easy. So what they do in Manual J is they basically do all the weird legwork for you on taking into account all those situations, so that they can just give you the HTM and you don't have to do all the complicated math behind it. So that's why that's why cooling HTMs are different, because basically it's outside the scope of our job to be able to do the equations required to find the effective temperature difference in cooling. So they give us numbers to work with that are darn close enough. Okay, so that's why it's different. And if you read your book, it'll tell you about that. So anyway, let's get back up to the windows, look at our construction again, and then find it on the table. So remember, table 2A is all windows and heating. We're done with heating, so we're not looking at table 2 at all, right? We're going to go straight to table 3. So our windows: double pane, operable, clear glass, wood frame, no external sunscreen, and Venetian blinds. Go to our table. If you remember, we found the first row of tables, basically. These are all like little mini tables in the table, right? The first set of tables is no internal shade. You never assume no internal shade unless you know for sure that they will not have internal shade. Okay, they will not put any drapes or blinds over that particular window. Otherwise, you always assume blinds unless you know they're doing drapes. Okay, and you're always going to do half drawn on drapes, basically. I couldn't explain to you why drapes are fully drawn or really even an option. I kind of always assume half drawn. But that does mean, again, pro tip, real world, right? If people are saying, oh, my house is really hot in the summer and it doesn't cool down on a 95-degree day, you say, do you close your blinds? Because if you close your blinds, the difference between closing and opening your blinds, let's just look at that real quick. Let's go on a tangent and look at that. You see these numbers? 24, 73, and 38. Those are the numbers we would use if we assumed no internal shading on a window. Alright, these are the exact same numbers we'd be using. This is the exact same situation, right? It's double pane, it's clear glass, and it's facing all the same directions. So this is the window you would use. These are the values you would use if you did not have blinds on the window. If you do have blinds on the window, you use these numbers: 16, 46, and 24. These numbers are about 25 or 30% less than the numbers up here. You lose 30%, roughly 25-30% less BTUs if you just put blinds halfway closed on windows. If you close the blinds all the way on the windows, you're going to drop it even more. Okay, because you're not getting the heat gain from the sun. And the most important windows are obviously the ones that are facing the sun at that given time. So, if you're having issues keeping a house cool when it's like 100-degree day, our houses aren't really designed for the systems to work on a 100-degree day. You can mitigate that by closing up as much of the windows and covering them as much as you can, because it will drastically reduce your heat gain. Okay, so anyway, just a tip you can give to people, because this is what we take into account when we do a load. So the way houses are designed are generally designed with blinds to be half closed on a design day. So our numbers.
Hey Chris, can I interview you for a second?
Of course.
So those horizontal blinds, where you can tilt them one way or tilt them the other way.
Mm-hmm.
I grew up in the Northeast, and we always said, hey, in the winter, make sure you have them tilting towards you as they go up, and then in the wintertime, in the summertime, have them tilting away from you as they go up. So as the warm air rises in the winter, it's not getting to go against the glass. And then in the summertime, as the warm air rises in the window, it's not getting to enter into the room because it's pushing away. Does that make sense, the way I said it? The blinds, one way or the other. So as warm air rises,
Yeah.
it either stays in the room in the winter or it stays against the glass in the summer. And we've been doing that my whole life.
I mean, it makes perfect sense. I don't know how much more it really makes a difference to have the blinds tilted in a certain direction, but if it affects the air current at all, then it affects the air current, right? So the biggest deal is, does it change how the draft feels to you at that window? If it does, then go for it. My understanding with blinds is basically the purpose of tilting it either way is so that you can block line of sight from different directions. But I mean, if you're blocking line of sight from the sun, whatever blocks line of sight better and keeps the heat, the cool air from hitting the window, and vice versa. In heating, you actually want the air to hit the window. Okay? In cooling, we'll get to, I'm not going to go on this tangent because it's manual T stuff. But the way you design in cooling is very different than the way you design in heating. Basically, in cooling, you're trying to keep the cold air away from the outside. And in heating, you're trying to push the warm air towards the outside because you're trying to affect how the heat moves in the house. So we'll talk about that a lot when we get to manual T. It's one quick class, but there's a ton of good information in it. So we'll talk about that. But yeah, whatever works. I mean, and it makes logical sense. I don't know if it would be a huge difference, but sometimes every little bit counts, right? So yeah, it makes perfect sense. Okay. So anyway, in our table, our proper numbers for our windows and cooling are 16, 46, and 24, right? And we already put those in our table because I wanted to note where they were, because even the rest of them we can pick that number, but this is all that table is for, is to find those three numbers. And remember, these are the three numbers you pick if you're not sure. You might get a couple questions wrong, but if you always put these three numbers, the majority of the time you'll get the windows right, because this is usually what I put down for windows, because this is kind of your most common window. I mean, it's just what it is. This is your most common window. So, even in real life, if you pick this number most of the time doing a simplified load out of J8, the abridged edition, you'll get this right. If you do a full manual J, these numbers change. But for a J8 simplified load, this is pretty much always the numbers you're going to use for even new houses with windows. So notice that under HTM, we just put those numbers here, right? We just put them right here. We don't do 20 times 16. We don't do 20 times 46. We don't do 20 times 24. The table, okay, that table does not have the U value in it. It has the HTM in it. These are the HTMs already there for you. The only math you may need to do with Windows, and I promise we'll do this on the next exercise so that you understand and you see how it works. I don't want to go off on the tangent now. But the only math you should have to do with these HTMs is if you have a particular type of window or door, you have a multiplier to account for that. And if you have insect screens, then you have to account for those. An insect screen will further reduce the heat gain through the window because it reduces the sunlight's ability to hit the window, right? So you have multipliers for full and half insect screens as well that you'll have to multiply this by to lower the value to account for that insect screen. But because we said we don't have any insect screen, we just put these numbers right over there, okay? And that's at least half your windows. It seems like most of the time insect screens are seem to be like a 50-50 thing on new homes. But if it does have an insect screen, then that's where you'd have to change something. But if it doesn't, these HTMs just go straight into our table right there in that order, and then the only thing we have to do to that is multiply our HTM in cooling times our area, and we'll get BTUs gained. So for our north facing window, it's 1,872. For our east and west windows, it's 2,760. And for our southern facing windows, it's 720. So north facing windows, notice our north facing windows have the most area, but the BTUs are kind of in the middle because north windows have the least amount of heat gain. Okay, a shaded window, if you have a shaded window, like you have an overhang that shades the window, the shaded portion of the window gets treated like a north window. It's the same thing. Okay, so a shaded window is the same as a north window. And if you guys are interested in the process for accounting for shading, I highly recommend you look at it. But again, we won't really learn it in the class because I don't want to spend a whole class going over this math. But that is on page 145 of your book. It tells you how to make the adjustment for a shade by an overhang. And maybe I'll talk about it a little bit one class if we have some time, but it's not really important. It's basically you take into account the angle of the sun hitting the window. If there's an overhang that keeps the window from the sun from hitting part of a window, then that part of the window gets treated like a north facing window and the rest of it gets treated like the window would otherwise. So anyway, that's how that works. And it's very important to take that into account, but again, most of the houses that are built don't have significant shading over the windows unless there's like a deck or something over it, right? And that's the most common situation where you have a shaded window. So you just need to remember that if you have a deck or something that goes over top of the windows so the windows never get any sun, just put those in your table as if it was a northern window. Even if it's on the south side of the house, put those shaded windows in with your north windows and you'll be doing it right. The only time you really have to do that calculation that's on that page is if only part of the window is getting shaded. But if you know the whole window is going to be kept from being hit by the sun, then you just stick that window as if it's a north window. Simple as that. So anyway, yeah, it's not too complicated, but I think it would still take most of a class for us to practice it, and I don't want to get that deep into it. I want to get all the basics first, so that if you guys want to do this in the future, you can, and if you're never going to use it again, I didn't waste too much of your time. I taught you the most relevant things. So anyway,
we're not gonna use it never.
huh? What? Say that again? You scared to repeat yourself? If you want to do this, I highly recommend it, okay? Being able to do a load calculation, I don't care what your position is in the trade. Every year I gain at least 1 or 2 students that has me do load calcs for them, okay? And then those students tell other people and things like that, and you can get a circle of people you know that you do load calcs for, and it's great to do. I meet other contractors, I do load calcs for them. Like I said, it's good knowledge to have either way, okay? It's very important knowledge to have either way, because understanding how the load calc gets done makes it easier for you to evaluate problems with the system without using rules of thumb. Because people will say, oh, you need this many BTUs per square foot, or people will say, oh, a room needs this many CFM per square foot. And those are all bogus ass fucking rules of thumb. Every rule of thumb you've heard about that is wrong. Guarantee it. I've heard them all, I've seen them all, and it never works out that way, okay? They'll work good enough, you usually won't get your ass handed to you over it. But if you do get your ass handed to you over it, it'll probably be pretty bad, okay? So it's just something to keep in mind. Anyway, yeah, I know that most of you guys probably won't bother doing it, but I highly recommend that if you find these things easy, it's simple, and you understand the whole process very well, practice doing it, because it's a very valuable thing that a lot of guys that even own companies aren't capable of doing properly. So it makes you a very valuable resource in the trade, which is what I'm trying to hopefully make most of you guys as valuable resources in the trade. Okay, that being said, we've got windows done, so now we're going to move to opaque panels, right? Let me pull this back up. We've got next thing is doors, right? We've got our windows done, so we need to go to doors. So let's switch back to our house real quick. Look at the doors we had again, just for posterity. Make sure we didn't mess anything up so far. Wood core, solid core wood, no storm. Find our doors, which are always the first thing in table 4. Construction numbers are 11. Start with 11. And we'll see the same thing. Solid core, and then our CLTD values, okay? Our cooling, load, temperature difference values are right here. 20 is 31, and that is your HTM. Okay, that's what you're gonna put in your HTM. So again, the reason we do 20M is because our temperature difference is 20 degrees. We designed for a 95-degree day, and our daily range is medium. Okay, so whether your daily range is low, medium, or high, your cooling, load, temperature difference changes, but for us it's medium, so our HTM is going to be 31. Okay, so again, we don't have to do any more math with that. We just take our 31, throw it into cooling, done, multiply that times our area, and that is our BTUs gained through the door in cooling. Now walls are where it gets tricky. This was new with manual J8 when they came out with manual J8. It used to be a little bit simpler to do walls. All the things were the same. But remember, our wall, and I didn't switch the screen again, did I? No, I didn't. So there's where I put it in Excel down there. the wood door, the number was 31, put in the value, multiplied it. Okay, remember to switch. Okay, blue beam. Right here, our walls, okay, remember our wall was 2x4 R13 insulation, wood sheathing, no board insulation, right? So this is our wall. With walls, you'll notice we have a U value here, alright, and then we have, all the way to the right, we have a little number, okay? So our U value's here, that's for heating, and then we have a group number for cooling, right there. Well, you have to pay attention. Remember, the bottom one is siding and the top one is brick. Okay? On all of these, the S means siding, the B means brick. So you have to pick the group number on whether you have siding or brick. We have siding, so our group number is C. Okay? You need to remember that. Your group number is C. And in your book, I should have it in here anyway. What page is it? You got to go all the way past table 4 in your book to get to these exposed wall CLTD values, medium color. Alright, this is all the way on page 165. So as soon as you get that group number with your wall, you need to go to the group number that you have for your wall, okay, or whatever else you're working on, and then you need to know if it's a wall or a partition. Usually, if you're doing a load with it, it's going to be a wall, unless it goes to a garage. If your wall goes to your garage, then it will be a partition. And a wall just means it's not exposed to, a wall just means it is exposed to the outside, and a partition means it's exposed to the inside. So even though the only time you use partitions is when the partition goes to an unconditioned space. And the biggest example of that will be your garages. So for your garage walls, you need to pick partition for the wall that goes between your house, your living area, and your garage. For pretty much every other one, unless it like faces like a shed that's built on the side of the house or something like that, but basically any wall that's actually exposed to the outside environment, it will be a wall. Alright, remember that. Walls go to the outside, partitions go to the inside. Okay, so you need to find your wall in your group number, then go over again under 20M, and then down here, that will be your HTM right there. So you need to line up this column with whether it's this row, with whether it's a wall or partition, and then make sure you pick the same column we pick every time, which is 20M, and then right there you'll get your HTM. So then we take that 26.5, we input it over here, 26.5 equals that times our area. Did I mess that up? Is that right? No, that can't be right. What am I doing wrong, boys?
You forgot to switch the page. We can see it.
Huh? Oh, I forgot to flip the page, but no, something don't seem right here. Something ain't right. What am I messing up? This can't be right. Just to be fair, guys, last year is the last time I used manual first time I used J8 abridged edition. It just doesn't seem right. CLTD Cooling load temperature difference. Am I forgetting a step? Let's look at the top of the table, right? Let's make sure I'm not messing something up. Top of the table gives us our formulas. Oh, yeah, no, I'm messing up. Fuck. Okay. Back up. I'm fucking you guys all up. Back up. Like I said, I've done manual J7 for like 10 years, and I'm the one who pushed to have us go into J8, and I screwed this up last year until I got this far, and I just screwed it up this year till I got this far again. Okay, let's back up a few steps. Forget everything I've said in cooling so far except for on Windows, because on Windows I'm right. And this is how you know you screwed up, okay? You know you screwed up when you get some crazy number like 20,000 BTUs lost on a relatively small house on walls. So I need you guys to stop, wipe your brain for a second, and forget everything I said on cooling, because they changed it in J8. And I know I should have remembered as soon as I saw CLTD. So what they did, god dang it. I don't really like the fact that they did this because it drives me nuts. But it is what it is. I guess it's a more accurate way than how we used to do it in J7. So going back, let's go back to our door. Let's start at a door because we still need to use that table again, but I want to start back at square one. Alright. So let's delete our cooling numbers. Okay. Well, no. The windows are still right. That's exactly how the windows work. The windows, they just give you the HTM. Okay? So everything is right on Windows. Alright? So in Windows, when you look at those numbers, those are your HTMs, and that's all you need to do with them. But on opaque panels, it changes. On opaque panels, what they do is they give you the cooling load temperature difference. So the cooling load temperature difference is the effective temperature difference in the summer. Okay? It's the effective difference. So since we have to take into account radiation and all that stuff, instead of just giving you the HTM like they used to, what they do is they give you the effective temperature difference, and then you still have to calculate your HTM. So on the door, let's go back to the door for a second. And if you get like 20,000 BTUs on your walls, you know you messed up, because that doesn't make any sense. A 31 HTM is crazy. I mean, it's bigger than our windows. Your HTM for your windows should be one of your biggest HTMs, bar none, because it has the biggest effect on heat gain and heat loss. So as soon as I got something over 16, I should have known. All right. So let's look back at our table and let's correct what I just told you. On your cooling HTM U value times table 4B CLTD difference. Okay? If you ever forget the formula like I just did, alright, that is the formula you need. Okay? So again, always pay attention to these formulas they give you at the top so that you don't make yourself out to an idiot. So what we need to do with the door is we have this 31 we found, right? Which is our cooling line design temperature difference. So even though the actual temperature difference on a summer day is only 20 degrees, the effective temperature difference from all the other sources of heat we have to contend with, sort of like the, you know how when you get the weather it says it's 80 degrees but feels like 92. Or with the wind chill, it's 20 degrees outside but it feels like -4. That's what we're doing basically, okay? We're saying even though it's a 20 degree day our effective temperature difference on this door during a 95 degree day with the sun out is going to actually be equal to it being 31 degrees difference. So we need to have this U value. I guess it's good I wrote down the U values on all of them, because we need to have this U value and multiply it by our cooling load temperature difference value. So it's going to be 31 times the U value. Alright, so the CLTD takes place of this CTD in calculating U values. So for heating temperature difference, there's no factors that we include, so the 53 stays the same. But with cooling, depending on what our thing is made out of and whether it's light or dark, but manual J8 really only gives us the option for medium colors. If you have very bright or very dark colors, you're supposed to use a full manual J equation to do it properly. But generally, colors are neutral enough, except for roofs, which they take dark into account, that you'll be okay doing a shortened load. So anyway, all the caveats aside, what we need to do is, now we know that the effective temperature difference for our door is 31. So we will put that 31 and then multiply it times the U value for the door, which is 0.39. So I take it back. Cooling went from being a little bit easier with J7 to being a little bit more complicated all across the board with J8. And I'm still, as you can tell, getting used to the way they do cooling now, because I've been learning and teaching out of J7 to do loads by hand forever, and on the computer it does most of these calculations for me, so I forget what I'm doing sometimes doing it by hand. So anyway, when you do that effective temperature difference, which is the 31, you do that effective temperature difference, which is the 31, okay? I'm going to erase that and do it again. Oh, God dang it. The effective temperature difference times our U value, which was 0.39, will give us an HTM of 12.09, and then we'll multiply that one times the area, and now we have real numbers. 254 BTUs gained through our door. Now let's do the same thing with the wall, and all the things I told you up until the math part is right, okay? So we go down to our wall. Bring it back on Bluebeam. Bring it down to our wall, which is, I already passed it. Dadgummit, this thing's moving so sketchy. Remember, we had our 0.091 U value, which we already put on our sheet, so we won't forget it. And then we go to the group number. So we go all the way to the end, right? So you guys should flip to page 165 real quick. We got our group number C. It's a wall. We get the effective temperature difference, the cooling load temperature difference of 26.5. So that number is not in HTM. We take that 26.5, go back to our Excel sheet, go over here, and we do our 26.5 this time. So for the walls, our effective temperature difference for a 20 degree difference is really 26.5 degrees. Multiply that times 0.091, and we will get an HTM of 2.41. That 2.41 times our area gives us 1,842 BTUs gained through our walls. Very good. Next is ceilings. So we will remember our ceilings were R30 insulation under a ventilated attic. I'm not even going to bother flipping to the house anymore because we flipped through it enough. Hopefully you've almost memorized this whole thing by now. So we find our ceilings, R30 under a ventilated attic, the construction number, and it helps if you look at the construction number too, right? If I look back at our sheet, our construction number was a 16B30, so we can find construction 16 right here, B, 16B30, R30, 0.032 is our R value. Our design cooling temperature difference is 55. So the effective temperature difference in your attic is 55 degrees on a design day. Why? Because the attic temp can get up to 130 degrees, dude. Your attics get super hot, which is why your ceilings have such a large effect. So it's going to be 55 times our U value. So, you know what? Let's do it on this sheet for fun. Let's just do it right here on this sheet. We're going to do arrow. Our HTM is going to be this 55 times our 0.32. So, equals 55 times 0.032. That is, let me pull out my handy dandy calculator maybe. I'll do it on the screen. 55 times 0.032. Yep, is going to be 1.76. So we go back to our Excel sheet then. Go back to our Excel sheet. That should have opened it. Yep, it did. And we do, again, it was 55 times 0.032, 1.76. That times our area gives us 1,478. Last thing is our floors. So, our floors were over an open cross or a ventilated crawl space, R13 insulation. Actually, I want to double check that one and make sure I remember right. Let's flip back to that. Yep. R13 insulation, carpeted over a crawl space. So we will find our floor, which was a 20P13, 0.068 U value. Our cooling design load temperature difference is equal as if it was 15 degrees, because remember, crawl spaces tend to stay cooler than it does outside, so that makes perfect sense, right? It's got no radiant heat from the sun or anything like that, and it generally ends up staying a little bit cooler because the whole crawl space is shaded. So our effective cooling load temperature difference is actually less than would be otherwise. So 15 times 0.068. So we will go back to our Excel sheet. Under HTM, we will do 15 times 0.068. That gives us 1.02. So 1.02 times our area, and we get 857 BTUs lost. Now, this is a somewhat efficient house. This house is not nearly as efficient as most need to be right now, right? But our square footage of this house, quote unquote, is only 840 square feet, right? So this is more like a big shed, okay? maybe a small, I mean, I've been in houses that were 840 square feet, but they're not super common these days, okay? This is a very old house or someone's very big shed is what this is. But if we were to stop here just for shits and giggles, if we were to start here, if we were to stop here without doing infiltration or internal gains or anything else, if there was nothing else in here that had any factor and this thing was sealed up super tight so there are no infiltration gains, so far our numbers add up to 14,824 BTUs lost in the winter and 9,783 BTUs gained in the summer. So that is, and this is not where you stop, so this is just for fun to see where the numbers are now. That is 17 BTUs per square foot in the winter and 11 BTUs per square foot in the summer. This is actually pretty close to a good relationship though. Somewhere close to a third higher on heating seems to be a common occurrence up to this point. Even though it's double the temperature difference in heating, cooling catches up because the effective temperature difference is actually higher than what we use. But anyway, up to that point, this is a good indication on whether or not you're close to right, okay? If your cooling number is higher than your heating number, you've made a mistake. If your heating number is double or more than your cooling number, then you might have made a mistake. You want to be somewhere close to this kind of ratio. It's usually pretty close. But of course, it depends, right? Depends on how many windows it has. The more windows it has, the more cooling load you have in relation to heating load. But the bigger your load goes up in general. If you're very energy efficient, then these numbers start to get farther apart because you've got a lot of mitigation for, infiltration and things like that. But really, your raw BTUs gained and lost through the construction are actually nowhere near some of the other things that come into effect, especially duct loss and gain. One of your biggest factors, especially in ductwork that's in an attic, is you lose somewhere between 10 and 25% of your load into the attic, into the ducts. You just lose all kinds of the BTUs the system creates just in the ducts, which is what makes ductless mini splits so efficient, right? It's one of the reasons you see those 20, 25, 30 SEER numbers coming up with ductless units, because there's a lot of factors where they don't lose BTUs that you would lose otherwise with a ducted system. But anyway, that's where we're going to stop, okay? I'm going to stop right there. I want most of this class to sink in, and then we'll do this all again from start to finish without me miffing it up. And hopefully you guys, at that point, you've been familiar enough and this is making enough sense that you guys can do a test on it. But that's basically all we're doing, okay? So it's important. The most important things to remember from tonight are where you find these numbers, okay? Where to get these numbers in your book based on your construction numbers, all right? So based on your construction numbers, where you get these numbers that we just found, and what the formulas were. So remember, going back to the top of our opaque panels real quick, top of table 4, you guys can follow along in your book by looking on page 147. For heating, it's the HTM equals the U value times the heating temperature difference, right? And for cooling, the HTM equals the U value times the table 4 CLTD value, okay? So you're just trading this for this to do cooling is how they're doing it now. The exception being windows. with your table 3 windows, notice here it says cooling load equals HTM times the load area. So this is your HTM for Windows. This, like I said, these tables haven't changed since Manual J7 at all. These tables have been basically the same for 40 or 50 years. Okay? These have not changed. I guess they dialed in cooling through Windows great a long time ago. Most of the changes in J8 from J7 were made to account for more energy efficient homes. So typically, your loads will be close between the two methods, but a manual J8 load will usually end up with a smaller system than the J7 loads used to do, except for when you have poor ductwork, and then it shoots that number right back up. So taking ductwork considerations into account is extremely important with J8. But anyway, remembering those okay, close the door, please. Just remember these formulas and where we got these numbers and where we got these construction numbers, and hopefully next class when we do one, just start to finish real quick together without spending too much time repeating what I'm doing. It clicks, and then I'll have you guys practice it on your own, and you can let me know if you're having trouble finding it. And I'm dead serious. When I give you your next assignment to get all these numbers by yourself, if you can't figure it out, don't just guess. If you don't know that you are getting the right answer, call or text me so I can help walk you through it, or I can get on the Google Meet and we can work on it together for a couple minutes. But I don't, and you know, we might have to do it, you know, next weekend, or we might have to work around the time a little bit so that we can do it like that if you're not comfortable doing it over the phone. But I would much rather you let me know that you don't understand it than get this wrong, and then the next thing wrong, and then the next thing wrong. And I'm going to be really irritated if we're trying to do a block load by ourselves and you call me because you can't find the construction number. Okay, that's going to be very irritating. It drives me nuts, but inevitably one guy a year does that to me. If you can't already find the construction number by the time we've gotten that far, you were supposed to ask a question a long time ago. So just ask the question. Okay? Feel free. I've told you guys 1,000 times. Feel free to give me a call or text me and tell me you don't understand something, because you guys haven't done it all year and it's irritating. Anyway, that's my rant. Otherwise, if you're good, I'm good. Have a good evening. We'll go over this one more time. You don't have to have it tonight, but you need to have it by the next class. Okay? After the next class, you should understand everything we just did perfectly. If you want some exercise work to do, I already gave you this sheet partially filled out before. Try and fill out all these numbers yourself. I put it on Google Classroom. Try and put all the numbers we just did yourself in there, and then on the beginning of next class, we can compare my answer sheet I already have right here to the answer sheet that you did. Okay? I'd be more than happy to do that. If you do not already have this, it would not be bad practice to do this yourself, because I will make you guys do this all yourself once. At least once, if not 2 or 3 times. Usually I try and do at least 2 or 3 loads. Make you guys do 2 or 3 loads by hand, because it's not that bad. I don't know if they still do it, but to get your HVAC and license in DC, you used to have to be able to do this. So there's another factor where you need to be able to do a load calc. But anyway, there you go. That's all I got. It's running late. You guys get some rest, and I'll holler at you later.
All right. Thank you.
Yes, sir.
Thank you, sir. Appreciate it.